Physics, as defined by Wikipedia, is a branch of science, one of the most fundamental scientific disciplines. The main goal of physics is to explain how things move in space and time and understand how the universe behaves. It studies matter, forces, and their effects. To start with the first in the list, collision is how the computer knows whether an object is touching another object, inside another object, or not touching at all. In other words, whether the objects are colliding or not. All objects in a typical 3D simulation are composed of points called vertices, connected by lines and filled with polygons. When a computer checks for collisions, it goes through all the points on an object and checks all the points on all the other objects and does some complicated calculations to check if objects are touching. Gravity is something everyone should be well acquainted with, unless you're somehow watching this in space or something. It pushes you down at a constant rate of 9.81 meters per second squared. In video games, that usually feels slow and isn't quite as fun, so developers will increase the gravity. In a lot of my personal projects, gravity is set to around 11 to 12 meters per second squared. In some games, gravity is a little more extreme. By extreme, I mean really extreme. Thanks to the game theorists, I know that in Super Mario 64, gravity is 26.12 meters per second squared. In Super Mario Galaxy, it's a flat 33 meters per second squared. And in Super Mario World, it's 36.42 meters per second squared. And in Super Mario Bros. 2, gravity is an insane 55.22 meters per second squared. That's about 5.5 times the gravity of Earth. To put this in perspective, taking off in a rocket headed for space, astronauts usually experience around 3 times Earth's gravity. And Mario can still jump about 5 times his height, even with the ridiculous gravity. I'm going to cover rigid bodies and soft bodies together since they're very similar. According to Wikipedia again, a rigid body is a solid body in which deformation is 0 or so small it can be neglected. The distance between any two given points on a rigid body remains constant in time regardless of external forces or movements exerted on it. Or to simplify, a rigid body is an object that can move but keeps its shape at all times. All the little cubes that you see are simulated rigid bodies. That big metal ball and the bullet thing are also rigid bodies. The bullet, however, is animated to go from one point to the other and ignore collisions that would normally make it stop or bounce. Remember collisions? A lot of what rigid bodies do is collide. If you look closely at the floor, you can see I accidentally set up the collisions wrong and some of the cubes fall through the floor. A lot of 3D programs such as Blender, Unity, Unreal Engine, Godot, Maya, etc. have different options for how rigid bodies collide. If you have a lot of rigid bodies in a scene, and they all have a lot of vertices, you can use a simple box, sphere, cylinder, or cone to calculate collisions instead of the actual object. Doing this makes it slightly less accurate, but not having to calculate all the vertices makes the entire simulation run way faster. You can apply different forces to rigid bodies, such as drag, friction, and gravity. Remember gravity? It applies here too. You can apply a more Star Wars style mysterious force to push objects around if you want. In the little example on screen, I made a quick program with a rigid body that has a force applied to it whenever I click on the screen. In a lot of games, if your character falls, they'll do a stop, flop, and roll. This is also a rigid body simulation, just with a few more steps. When a character rolls like this, it's called a ragdoll simulation because they flop around like a ragdoll would. Ragdoll physics are pretty simple. Characters in 3D movies or games have bones, a way for the animators to move the character's model. To get a ragdoll, you add a rigid body to each of the bones, tell the computer to not let joints swing backwards, and there you have it. Essentially, a soft body is a rigid body, but each of the vertices is also a rigid body, with a mysterious force to keep the object from collapsing. The mysterious force is usually a simulation of pressure, keeping the object at a constant volume. Soft bodies are much more common in film because they take so much processing power to simulate. It's uncommon to see them in video games because they need to run fast, so they can't spare the processing power to simulate soft bodies. Now, for a little bit of a pun, one of the soft body's most common uses is to simulate skin, muscle, and fat, the soft parts of the body. Cloth is basically a soft body that's been opened up, so it doesn't have pressure, but it's still affected by drag, friction, and gravity. If you couldn't guess, cloth is usually used for clothes, curtains, sheets, blankets, and other things made of cloth. Particles have many different forms, so I'm going to start with the basic particle. Particles come from an emitter and can be affected by several different forces: drag, friction, gravity, the mysterious Star Wars-like force to make them move, and a few others. Particles can be rigid bodies or soft bodies, but particles will often be in groups of hundreds and even thousands, so it can really slow down the computer. Particles have a set amount of time that they can stay alive, their lifetime. The lifetime can be set to infinity, a set number of frames or seconds, or set to end when the particle touches an object. Particles don't have to move, and one of the common uses of non-moving particles is hair, grass, and leaves. These static particles are emitted from an object, but then they just stay there. Particles are also used to simulate fire, smoke, water, and other gases and fluids. If you've gotten past like first grade, you'll know that water is made up of billions of little H2O molecules that like to stick together. Computers aren't quite to the point where they can simulate water perfectly, so we only use about 1 million particles and fill them in to make a believable fake water. Fire and smoke are simulated very similarly. Fire and smoke are simulated like water with particles that float up and away instead of falling like water would. Other gases and fluids are simulated in more or less the same way as smoke, fire, and water, just with the speed of the particles, particle lifetime, and other settings changed. Physics are far more complicated in real life, but computers aren't yet capable of simulating everything, so we simulate what we can, and it usually looks good enough. Thanks for watching! Here's a short montage of some cool physics simulations.